So in this video here, I will talk about Bernoulli's equation. We have a functional physics group where I was requested to make a video on this. So I'll just run you through some basics, hopefully open you up to a better understanding of this equation. So it relates pressure, velocity, and elevation or height of a fluid. It can be used to predict lift in planes. It can be used to calculate the time it will take to empty a tank. It has many applications. So that's the equation. It has three pressure terms that you're supposed to be familiar with, and they all add up to a constant. So you have static pressure, which is the pressure of the fluid. You have your dynamic pressure, which is pressure as a function here of velocity and density of the fluid. And you have your hydrostatic pressure, which is a function of elevation or height, and also gravitational field strength, acceleration due to gravity. So remember, those three terms will add to a constant along a streamline. It can be written in other forms as shown there. So those three terms are actually representing energy. So you have pressure energy, kinetic energy, potential energy. Those different forms of energy, they add up to a constant along a streamline. So this confirms our conservation of energy, law of conservation of energy. Energy cannot be created or destroyed. It can change from one form to another. So remember, these three will always add up to a constant along a streamline, which is just a path that a particle can take as it flows through a fluid. So let's imagine here a liquid which is passing through a pipe from a point where the pipe has a larger area to a point where the pipe has a smaller area. So remember, the three terms will add to a constant. So here, if you imagine a streamline, we have 2 points and the particle flows through point 1 through point 2. So we can write an equation for the particle at point number 1 and write an equation for the particle at point number 2 and equate these two, because these two equations will always add up to a constant along a streamline. So we can equate as shown there. What we can do here is, since here as we move from point number 1 to point number 2, our height is not going to change significantly. That means that term is going to be constant, and hence we can cancel it out. And when we do so, if we rearrange the equation, putting our pressure terms to the left, we end up with that equation where we have a P1 minus P2, a pressure difference there being equal to that term to our left, to our right. Okay, so that equation, with that equation in mind, we must also be familiar with something called the continuity equation. Basically, we are saying the mass is constant. The mass of fluid flowing through point number 1 is equal to the mass of fluid flowing through point number 2. So our mass is constant, and but if you look at that arrangement that we have, it should be intuitive that as the fluid moves from point number 1 to point number 2, as you can see, it's moving into a smaller area there. So in order for the masses to balance and always stay the same, it should suffice that the velocity must increase. The velocity of the fluid at point number 2 should increase. So with that in mind, we can have our continuity equation that says velocity at point number 2 is proportional to that term, area 1 divided by area 2 multiplied by velocity 1. So here you can see that if the area decreases, which is A2, then our V2 is going to increase. So as the area decreases, the velocity is going to increase. So as the fluid moves from point number 1 to point number 2, its velocity is going to increase because the area there has decreased. So we can now take a V2, substitute A1 over A2 times V1 into this equation here. So when we do so and rearrange, and I remember V2 is larger than V1, when we do so, rearrange, this is what we end up with. So there is a pressure difference there, which is pressure 1 minus pressure 2 is equal to the terms to your right. But you can see that there is a direct proportion there between the velocity and the pressure difference is there. So when the velocity there increases, as what happens as you move from point number 1 to point number 2, then the pressure differences are also going to increase, and it must follow that P1 must be less, P2 must be less than P1 for this pressure difference to increase. So we can only make P2 smaller in order for us to have this balancing out. So when your velocity increases, the pressure difference increases, meaning that P2 is becoming smaller. So meaning that as you move into point number 2, your pressure is going to decrease. So as your velocity increases, remember the pressure is going to decrease. This is counterintuitive, as you would expect that when you increase your velocity, your pressure will also increase, but this is not what happens. So for this video, this should be enough. I'll continue in a different video if you're interested in knowing more about this equation and its application, and also some calculations that we can do. So there is the Bernoulli's principle that can be coined as follows. So for horizontal flow, we saw that here an increase in velocity must be accompanied by a decrease in pressure. This is what would allow things to balance out in our equation. So Bernoulli's principle, one way to put it together is to say for horizontal flow, an increase in velocity must be accompanied by a decrease in pressure. So we'll pick it up from there and see what else follows. See you in the next video. So we're going to look at some of the applications of Bernoulli's equation. We're going to look at aeroplane wings, how they can generate lift. So when you have a wing, there is going to have two regions. Above it, there's going to be air flowing at a high velocity. And you should remember that when you have high velocity, you are going to have low pressure because the energy there is going to, required to increase the velocity is going to come from the energy that would otherwise have been used to increase your pressure. So high velocity, low pressure. So you're going to have low pressure there, and below where you have low velocity, you're going to have high pressure. So air is going to try to move from high pressure to low pressure, and in doing so it will generate lift. In Bunsen burners in chemistry, you're going to have the same here. This is what enables Bunsen burners to be efficient and enable complete combustion. Here's what would happen when your gas tap is opened. You're going to have gas moving at very high velocity. It flows into the burner as shown there, and as it moves up there, it's going to create there's going to be high velocity, and that will create a region of low pressure, which helps to draw air in, enabling your burner to work efficiently and have a complete combustion. There's a device which can be used to measure pressure there, where this equation is applied. So let's look at that. We have 2 points there, and we can calculate here our flow rate, which is equal to the velocity times the area. So this device is used to measure our flow rate Q in that case. So if you still remember our pressure drop equation that came from the Bernoulli's equation, here you see that we can rearrange it. We can easily rearrange it for velocity, where we end up with this, and we can substitute our V1 into that flow rate equation, and that is what we end up with. So you can predict flow rate given the area or the dimensions of those 2 points. So you need area, you need the pressure differences. So that's one place where your equation can also be applied. You can also here predict the time it will take to empty a tank. So when you have 2 points there on your tank, you can equate those 2 points as before. That would be a streamline there. And for this one, that pressure term is going to go because both points are going to be exposed to atmospheric pressure. So it's atmospheric pressure that's acting there. And another term is going to go here inside the tank at point number 1. The velocity near the surface there, assuming the tank is large enough, is going to be near 0. So this term will go, and the remainder can be rearranged here. If we take h to be the distance between point number 1 and point number 2 there, then we can rearrange and end up with the velocity of the liquid as it leaves the tank being equal to that term. So these are some of the few applications of Bernoulli's equation. Hopefully this will help you this helps to spark more interest in you to look into this further. So I'll meet you in another video. You can always join our WhatsApp groups so that we can have further discussions concerning the applications of Bernoulli's equation.